There we go. So this is an approximation. And you might need to move your sidebar in order to see this on the right side of the screen. And there's a question in the chat. Newton's method, let's see. What did we call Newton's method? If I remember correctly, and well, I should remember, but this has been a weird half a year, so hopefully I get this correct. So Newton's method is a way to approximate the zeros of a function. So it's a way to approximate finding exactly where this function crosses the x-axis. And that's a little bit different than what we're doing with this area problem. Oh, that's fine. It was a good question. That one involves using the slope of your curve to approximate the zero. Okay, so back to our approximation. In order to approximate this area, we'll just add up all the areas of the rectangles. So that's, A1 plus A2 plus A3, and then 4 and 5. Okay. But then each of these areas are just rectangles that we can find the area for. The first one has width x1 minus x0, and height here, so this is the function value at x1. So let's see if we can squeeze this in. So it's f of x1, and then x1 minus x0. And then the second rectangle, its height is here. So that's the function value at x2. And then the width is from here to here. That's x2 minus x1. Okay. And, well, we would just continue. Maybe I'll finish writing it out. So it's f of x3 for the height of the next rectangle. And then x3 minus x2 for the width. And then we have f of x4 and that width is x4 minus x3. Let's see if we can squeeze it in here. And then area 5, since it was a flat rectangle, not really a true rectangle, its area was 0. Yeah, so in the chat again, Jesse, you're correct. This is a Riemann sum. That's right. Okay, so a little bit more notation. This ties it back to Riemann sums a little bit. Getting a little cluttered, but I guess there's no helping it. This distance, this width between x1 and x0 is usually what we called in calculus delta x1. So delta is the symbol that we use in math to represent change. So this is something like the change from x0 to x1. And this simplifies the notation a little bit. And then the third rectangle. Oops. Maybe separate that a little bit with a box. Okay, so this whole process of approximating, see if we can get things lined up. This process of approximating areas is something that you probably worked on pretty hard when you took Calculus 1. Does anyone have, or does anyone remember how we would improve our approximation for the area?
More rectangles.
Right. So if I wanted a better approximation, I could divide up my original area, this one, into more and more rectangles to get better approximations. Let's see, did that actually fit in? Yes, perfect. Okay, so this idea of dividing into rectangles and then adding more and more rectangles for a better approximation is what led to the idea of an integral. So an integral was defined to be the limit as n goes to infinity of this Riemann sum. So you probably saw something like this in Calculus 1. If you don't remember all the details, you don't have to worry about it here today. I just want to get you thinking. Okay, so this sum using sigma notation is exactly the kind of sum that we did up here, where we were adding our areas of rectangles, but now I'm just using the shorthand sigma notation. And this number on top tells me how many rectangles are in my sum. And I'm going to take that number to infinity, and what we get is the integral of our function. Okay, so that's where I want to stop with our review. Does anyone have questions?
Yeah, on the test,
Uh-huh.
do you care if we put the A5, like if there was a situation like that? Because we never did that.
You mean the last one that has an area 0?
Yes, yes, sir.
If you left it off, I wouldn't count off any points. But this is really a Calculus 1 kind of thing, so I don't think I'll ask this particular question on your exam. Okay, so that was, like I just said, a Calculus 1 kind of thing. What we want to do today is not necessarily any more complicated, but we're going to go up in dimension. So what I mean by that is this shape is two-dimensional. It's flat. It sits on this piece of paper. And what I want to do today is go to the third dimension and talk about volume. Let's see. Here. Okay, so the first thing that we're going to talk about is slicing by parallel lines. And I'll explain as we go along. So I mentioned, oops, I shouldn't say lines here, excuse me. Lines is what we did for a two-dimensional figure. We're going to be slicing by planes. So before, with this two-dimensional shape, we used vertical lines to divide up our area into simpler areas that we can actually compute into rectangles. But in 3 dimensions, lines can't divide a 3-dimensional shape. And let me go ahead and start drawing here. And I will do my best with this 3-dimensional drawing. Okay, so imagine I've taken my XY plane and I've kind of turned it up and out of the page. And I'm going to draw a simple kind of 3-dimensional shape. So it's going to be a kind of a kidney bean shape. That's been turned into a tube. So let's see. So hopefully that gives you a picture in your mind of what this might look like. Since I'm drawing, just spur of the moment with a pen, my illustrations aren't going to be the best. So I definitely encourage you to take a look at your textbook because they do a better job of doing computer-generated graphics there. But just imagine that this is a tube, kind of an irregular shaped tube, that's sitting above the x-axis and extending in this direction. So maybe you take a pipe, an actual pipe, and then it's been kind of smashed a little bit, like this. So if I wanted to find the volume of this shape, dividing it up using lines wouldn't work because this is 3-dimensional. If I draw a line through it, it's just like stabbing through the middle. It doesn't separate it. Instead, what I have to do is use a plane. Let's see. Like I said, I'm doing my best here with our 3 dimensions. So imagine I've drawn a plane through this figure, and where it intersects here in the middle is another little kidney shape. So this shape is actually sitting on this plane, and it's where this plane has gone through my 3-dimensional shape. So what I've done is I've made a slice with a plane. Perpendicular to the x-axis. And I'm not going to be able to make as nice of a picture as I did with the two-dimensional shape, but what I want you to imagine is that I could draw lots of planes on this three-dimensional figure and divide it up into segments, just like we divided up our our two-dimensional figure. So I drew lots of vertical lines. And in this three-dimensional realm, you can imagine I've drawn lots of planes to divide this up. And what we need to think about is that each of these slices is going to have a little bit of thickness. So just like my rectangles had a width, I'm going to have a width for each of my slices here. So let me see if I can find some space to draw one of my slices. So they look like little kidney shapes. And it's going to have just a little bit of thickness. And this is kind of a magnified view. There's the back of the shape. I'll draw it with a dotted line. So here's this line here that's going to represent the width, or in 3 dimensions, we often call this a height. Okay. And in our 2-dimensional setting, we call all of these widths delta xk to represent the change in this direction. So that's how I'm going to represent the height of this particular slice. So it's on the x-axis. I've taken this segment and I've set it over here on the paper. You can imagine that. And I'm drawing it in a blown up view. And then we also need to talk about the area of the surface. So where my plane has made the slice, we get an area. And I'm just going to represent this with a function, a, at this particular point. So this is where my slice is, at xk. Where should I draw it here? Maybe there. Okay, so how can I find the area of this shape? Or what kind of shape is this? So in 2 dimensions, we had a rectangle. In 3 dimensions, we call this kind of shape a cylinder. So when I say cylinder, that probably brings the image in mind of like a soda can, which is actually a special kind of cylinder called a right circular cylinder. And this is a more irregular kind of cylinder because its base in cylinder language is this kidney shape, but it still just has a little bit of height. So I have like a base that's been extended, just like a soda can is a circle that's been extended upward. Does anyone remember how to find the volume of any cylinder? Well, it works the same as the right circular cylinder. It's the area of the base times the height. So going to the picture, if I wanted to find the area, I would take this, my function for the area, a of xk, and multiply by this little height. So just like before, where we had these rectangular slices, now I've divided up this three-dimensional figure into cylindrical slices with little tiny widths. It's hard to see on this picture, but you have to kind of imagine it. I do, like I said, encourage you to take a look at this section in the textbook because it does a much better job with three-dimensional graphics than I can do on a piece of paper. Okay. So, continuing on, if I wanted to approximate the total area, and I need to draw in a couple more tick marks in my drawing. Let's say this figure extends from this tick mark A to this one B on the x-axis. If I wanted to find the total approximation, I would have to add the volumes of all of my little cylindrical slices. Okay, so just writing that out using sigma notation, I would say the volume, and I'm going to use a squiggly equal sign for approximately, is approximately the sum of all of these areas, AXK times the widths, delta XK. And let's just say I've made n slices. Okay, so how could I improve this approximation? So if I have n cylindrical slices, how could I get a better approximation?
Use more slices.
Right, that's right, Amelia, and I couldn't see who just commented. So add more slices. Okay, so if I take this idea to its natural culmination, to its natural limit, the idea of adding more slices, what I'm going to do is exactly what we did before with our Riemann sum. So we took a limit as n goes to infinity, where n represents the number of slices. So this notation gets a little hard to read maybe, because now I have sigma and a limit. But just like before, this limit of a Riemann sum is really an integral. So this is really the integral from A to B of my area. So we've taken an approximation, and by adding more and more slices, more and more cylinders, we get an exact volume. Okay, any questions about this idea? Let's see, so we have 11 minutes left. That should be plenty of time to actually do a concrete example. Okay. Let me write out the problem, and then we'll think through how to find the volume. In this problem, I'm going to have a 3-meter high pyramid. And it has a square base. Three meters on a side. Okay, so hopefully you're starting to get a picture in your mind. This is about as square of a pyramid as you can get. Its base is a square, and the height of the pyramid matches the length of the sides of the squares. But let me just elaborate a little bit more. The cross section, so remember a cross section is a slice of the pyramid. But the cross section of the pyramid perpendicular to the altitude, and I'm going to draw a picture in a second to illustrate. Is actually a square. Oops. And I want to talk about the altitude, x meters, down from the tip or the vertex. And it's also a square and it's going to be X meters on a side. Okay, so kind of a lot to process in writing. And we want to find the volume. So in order to really understand what's going on here, our first step is going to have to be to sketch a picture. So sketch a picture of this solid shape and a cross section. So I'm writing out these steps because these are the same kinds of steps that you're going to have to do when you're working on the homework. So what I'm going to do is start the same way as my example earlier. So I have my XY plane, but I've sort of turned it up on its side so that we can better get a three-dimensional picture. And instead of drawing the pyramid with its base, I don't know, sitting on the paper and then extending upwards, I'm actually going to put the tip of my pyramid, the vertex, here. And I'm going to have the base of it extending out this way. So remember, it was 3 meters tall, and the vertex is going to be here. And the base is 3 meters on a side. So I need to draw a square base. But remember, this is in 3 dimensions, so I need to draw it in perspective. Something like this. Oops. Excuse that extra line. And then the final line is actually hidden from us. It's behind the shape. So I'll draw it in a dotted line. And then in the problem, it talks about a cross section that's X meters down from the vertex. So what I want to do is go along the x-axis. Let's just pick a point, maybe here. We'll call that X meters. And I want to draw a cross section. Let's see. So a cross section of the pyramid is going to be another square. And this one is going to be a little bit smaller than the base. Something like this. So this is down from the tip, X meters, and each edge of this new square cross section is also X meters. And I left off a couple labels earlier. The base is 3 meters on a side. So the next step is to, now that we have a picture, some sort of picture, and a picture of a cross section, I need to find a formula for the area of a cross section. So I need to be able to write a of x is equal to, well, whatever it needs to be. So if I go x meters along the x-axis to here, what's the area of the cross section? Well, this is just a square, right? I didn't quite hear the beginning of what you said. Okay. Not sure what you said still. But the area of this slice, which is x meters on a side, it's a square, is just x times x, or x squared. So just like the area of the base is 3 times 3, this one is x times x. So that's step 2. And then I need to continue setting up the integral for the volume. So the next thing I need to do is find the limits of integration. And this one we can just read off from our picture. We've placed the tip of our pyramid at 0, and then the base of it is sitting 3 meters away along the x-axis. So that means our limits of integration are going to be 0 to 3. Okay. And then step 4 is to put all of our information together. We need to actually integrate to find the area, integrate to find the volume. So here's our integral formula from before. We're going to integrate our area function for our cross sections using our limits. Okay, yeah, I think I am running a minute or two over. So if you have to leave right now, that's fine. So let's set up that integral and then do it really quick. Should only take a moment. Okay, so there's the formula, and we know our limits are 0 to 3. And then our area function is x squared. What's the integral of x squared? Anyone?
1/3 x cubed.
Good. And since this is a definite integral, we actually have limits of integration. I'll use the vertical bar notation that you've probably seen before in your Calculus 1 class. And what this tells us to do is to plug in the upper number and then subtract what we get when we plug in the bottom number. So this is 1/3 times 3 cubed minus 1/3 times 0 cubed. So 1/3 times 0 is nothing. And 1/3 times 3 cubed is 1/3 times 27. So this comes out to 9. And since we're talking about a word problem here, we should go ahead and include our units. And this is volume in meters, so it's meters cubed. Okay, any questions here at the end of class? I guess not, since no one's saying anything. So I'm going to go ahead and stop the recording.